So we have here the confidence interval for mu1 minus mu2. If we're trying to find an interval for the difference in the population means using two independent samples, of course you have to pick a particular confidence level. So the level C confidence interval for mu1 minus mu2 is given by this formula. Now if you're in my classes, I always let you use the TI-84, TI-83 calculators, and you can use the two-sample T interval and not have to do all the detailed computations of this by hand. But I would like you to kind of recognize how this is very similar to all the formulas. Your confidence interval is always your statistic plus or minus your margin of error. The statistic here is the difference in the sample means. And then your margin of error is always this critical value times your measure of standard deviation for your statistic. And in this case, the measure of our standard deviation of the statistic is that square root with the combinations of the S's and the N's there that we saw previously. And then your critical value, we're talking about a t-distribution, so it's that t star that traps C% of that t-distribution between t star and negative t star. And then to find that, you have to have the appropriate degrees of freedom to be talking about the particular t-distribution. Again, you could use the conservative approach and use the smaller of N1 minus 1 and N2 minus 1, but it's much more accurate to let software compute the more accurate degrees of freedom. So if you were going to do this by hand, you could find that t star and go through and use the formula and do this, but we have a two-sample t interval procedure on the calculator that I will show you in an example. So let's look at an example. So a statistics student thinks that the residential students on her campus study more on average than the commuter students. She selected a random sample of 25 residential students and found that they reported studying an average of 8 hours per week with a standard deviation of 2.1 hours per week. She selected a random sample of 20 students and found that they reported studying an average of 7.25 hours per week with a standard deviation of 2.6 hours per week. Find a 95% confidence interval for the difference in the two means here, the average hours per week studied between the residential and commuter students. So for mu1 minus mu2, where those mu's are the average hours per week for the residential and the commuter students, the average hours per week that they study. You'll notice here, I'll point out, the sample sizes are not the same. They don't have to be. You don't have to have, they call it a balanced sample or a balanced study if your sample sizes are the same. They don't have to be. There might even be a reason. Maybe there's more residential students in the population than there are commuter students in the population, and you want your samples to kind of represent that. So you can have different sample sizes. That's why it's important that we distinguish the difference between N1 and N2. So I've got this one. I just did the screenshots of the calculator here of what I would do. So you hit the stat button on your calculator and you go over to the test, the same place we get the z-test and the regular one sample t-test and all of these things. And you scroll down. You got to go pretty far down on the TI-84. It's, I guess, the 10th thing down because you got 1 through 9, and then number 0 below it is the two-sample t interval. That's what we want. We're going to do a confidence interval. We're using the sample standard deviation, so it's a t procedure. And in my class, we'll never use the two-sample z. You see that it does exist there if you happen to know the sigmas, but in the real world, you pretty much never do. So we're using the two-sample t procedures. You select that, and then you get menus. It looks very similar to the menu you would get for the one-sample t interval, except you have two sets of information. But at the top, you have to pick whether or not you have the data or you just have the statistics. Here we have the statistics, so we would select that, and then you enter the values. And the distinction here, you could pick either, you could let the residentials be group 1 and the commuters be group 2, or you could reverse that as long as you keep straight which is which, and think about that in your interpretation. But I've entered in the order it came in the problem here, the residential students as group 1, and so their average was 8, so x bar 1 is 8, and their standard deviation was 2.1, and then N1 was 25. And then we had 7.25 as the second mean for the commuter students. And then 2.6 was their standard deviation, and 20 was their sample size. And the menu's kind of long here. You have to scroll down and keep on entering information. You have to do the confidence level. We're going to do 95%, it's 0.95. And then it asks, this is talking about how it computes standard deviation when it does computations, whether or not you want to pull the standard deviation. If you have reason to believe that your populations have the same standard deviations, you can do what's called pulling them. But in practice, it's recommended you always choose no here if you have software that can do it, because it's going to be more accurate in general computation. So I would always leave that at no. It's an easier computation when you do it by hand if you pull the standard deviations. It's a smaller formula for it, And so they make software that would match those type of computations. But honestly, when you have the software, it's more accurate to choose no to that. And other software, like maybe use Excel, it calls it equal or unequal variance. You would pick unequal, and that's like picking no. We're not going to pull the standard deviations. And then you calculate, and you get your confidence interval. Okay? It'll also tell you the degrees of freedom that you would get if you use that formula. And it's not a whole number from that formula. You get 36.2 something in this case. Sort of a combination of the two there, but much less than just adding the two together. So our confidence interval wound up being negative 0.7 something to 2.2 something. In particular, I made a note here, 0 is in that interval, which means we're 95% confident that whatever mu1 minus mu2 is, it's in this interval. So for all we know, it's 0 and there's no difference. Our confidence interval is showing us that we don't have really strong evidence that there is a difference between them. We're going to test that more formally with the hypothesis test here in another example, in example 2. But you can actually, in this two-sample case, use a confidence interval to do a hypothesis test. We're 95% confident that we get this interval which has 0 in there. That's like doing a hypothesis test at the 5% level. We do not have significant evidence at the 5% level that 0 is not in this interval here. So we are going to do the two-sample t-test. I'm going to do the same problem we just did, but do it as a two-sample t-test here in a second. So if you do the t-test, you have to compute the t-statistic or have your software compute it. And again, that's your statistic minus your parameter divided by the standard deviation of the statistic. And our statistic is x1 bar minus x2 bar, the difference in the sample means. And then we have this measurement, this square root, that is our approximation using the sample standard deviations of this combined standard deviation for the difference in the sample means. And our parameter is 0 from the hypothesis. Our null hypothesis is that mu1 minus mu2 is equal to some hypothesized value, usually 0. Okay? And in this case, we're going to say that it is 0, and so that's the statistic we would get. You compute that, and then if you have the appropriate degrees of freedom, which again, we're going to use technology and use the more accurate ones, you can compute a probability using the area under the t-distribution. And it could be a one-sided or a two-sided test, depending on whether your alternative hypothesis is that mu1 minus mu2 is greater than 0, less than 0, or not equal to 0. So let's look back at our studying example. So it's the exact same paragraph at the top. You got a statistics student that thinks residential students are going to study more than the commuter students, and we have the same numbers as the previous problem. We have a sample from the residential students of size 25 with a sample mean of 8 hours per week and a sample standard deviation of 2.1 hours per week. We have a sample of size 20 from the commuter students, and we have 7.25 hours per week for the mean and 2.6 for their sample standard deviation. I think I left out the commuter on that sentence there. She selected a random sample of 20 commuter students. I may have made the same mistake on the previous slide. You have the residential and the commuter students. So this time, instead of doing a confidence interval, let's do a hypothesis test. And let's use that standard of 0.05 as the significance level, the cutoff level. So conduct a hypothesis test to see if there is evidence that she's correct, meaning that the commuter students study more on average than the residential students. So the way we set up our hypothesis is going to depend on which one we call group 1 and group 2. And of course, that's our decision, but I'm going to go in the order they were presented and let group 1 be the residential students and then group 2 be the commuter students. If I do that, then my alternative hypothesis, we think that the residential students are going to study more than the commuters, so it'd be mu1 is greater than mu2. So your alternative, or your null hypothesis, is always mu1 equals mu2, or equivalently, mu1 minus mu2 equals 0. Your alternative here, in this case, if this is the way I've labeled the groups, would be that mu1 is greater than mu2, or mu1 minus mu2 is greater than 0. Sometimes you compare them to 0, and sometimes you compare the mu's to each other, as I have here. So to do this, we're going to, as always, hit the Stat button, go over to the Test menu, and look for two-sample t-test. It's number 4 here on my calculator, the two-sample t-test. And you get these menus. If you've just done the previous problem that I did with the confidence interval, all the information is still in here stored, and you don't have to change a whole lot. So we have the stats. we enter in x1 is 8, the x1 bar is 8, the sample standard deviation for group 1 is 2.1, and their sample size is 25. X bar 2 is 7.25, the standard deviation number 2 is 2.6, N2 is 20. Scroll on down and you have your alternative hypothesis where you're comparing mu1 to mu2. That's the way the Texas Instruments calculator does it. So we're going to choose greater than. Mu1 is greater than mu2 was our alternative hypothesis. Always leave pooled on no when you have software that will allow you. And then it's blacked out there, but it was because it was blinking on it. Calculate. I clicked calculate. You can draw if you want to see the picture as well. And you'll get your test statistic that it computes using the formula that I had on the slides. It's 1.05 if you round it, and the p-value is about 0.15. Okay? So I have the interpretation at the top. 0.15, that's larger than 5%, so we don't want to make that type 1 error. We would fail to reject. Okay? If whatever our significance level is, if our p-value is larger than that, that means our evidence isn't strong enough. We'd fail to reject, and there is not significant evidence of what we were trying to show in the alternative hypothesis there, that residential students study more per week. So that's an example of the two-sample t-test. So basically, if you understand the one-sample t-test and t-interval, the two-sample, it's just you're comparing mu1 and mu2, and the procedures are very similar. If you're doing the computations by hand, the formulas are a little more complicated. You're replacing x bar with x bar 1 minus x bar 2, and you have a more complicated formula for the standard deviation involving the square root of a combination of the data from the two.